You guys want to see something pretty cool?
Yeah.
Check this out, guys. Let me share my entire screen. In these two terminals, I'm SSH'd into each of these two robots. Let me make sure you can see the robots. Put them there. Everybody see that?
Yeah.
Yeah.
So those are Robot 1 and Robot 3. Don't ask what happened to Robot 2. I don't like to talk about it. So we have a motor driver node for Robot 1 running in this terminal, and a motor driver node for Robot 2 running in this terminal. Both of them are currently running a ROS node. Now, when that happens, according to the programs that I wrote, when those nodes are running, the system is able to identify each of those robots. The way that it identifies them is by their Linux username. So that's why you see up here, Robot 1 is the Linux username for this robot, and Legion 1 is the host name. I just put Legion 1 so it's easy to remember, right? So Robot 3 is the Linux username here. That gets scraped from Linux itself, and used as the namespace for these robots. Now, over here, this is not SSH. This is my actual terminal, and I'm going to run this. This is, of course, after pasting these commands, which are going to become very familiar to you. Just making sure that localhost only is off. All the robots can talk to each other. Making sure ROS domain is set to 0 for all robots so they can talk to each other. Sourcing your setup.bash in Jazzy, and sourcing your setup.bash that was created from your actual files. Now, I'm going to enter this, and it's going to open my teleop program. It took forever to get this looking the way I wanted it to.
That's good.
Now it's asking me, it says available robots, Robot 3. Well, where's Robot 1? Put in refresh, and it's going to show us we got Robot 1 and Robot 3 are available, right?
Yeah.
But I'm still not controlling any robot. So let's select a robot. I'll put Robot 1. And now the active robot is Robot 1, and we got some movement there.
Wow.
And now this is the fun part. Now if I press M, and then I put Robot 3, using the same teleop, and all of a sudden,
No way. That's pretty sweet.
Look at him go. You notice that each of those has a camera on it, right?
Mhm.
Well, I built a UI that goes in your browser. I have two different versions. You can see this, everybody?
Yeah.
So I have two different versions of it. This is one version, and this is the version using another stack. But basically what you see is you see your controls. This is where you will see the view from the robot that you are currently controlling. And these are all going to be different robots. So you can select Robot 1. All the robots on the network or that are broadcasting ROS nodes are going to show up there. The next step is obviously going to be putting this on Wi-Fi on the actual internet so that anyone can just log in, see which robots are available, and take control of them.
Nice.
How cool would it be to play virtual hide and seek with robots like that?
You do it in my front yard. I got plenty of room, and it's all paved.
Yeah, I think that'd be a lot of fun too, because it's like we might not be able to meet up physically, but we can definitely play hide and seek.
Yeah, you guys own an oscilloscope?
I got one.
Because I know you can figure out different frequency bands with that.
Oh, you have no way to get the wireless signals in the scope. For that, you'd want like a spectrum analyzer and SDR. SDR you can get for like $30 on Amazon. That's I've used like a $30 SDR to like do protocol analysis of like our wireless protocol that we used in our products that work. It works great because it's like it doesn't need to be a precision piece of test equipment because you're not interested in getting exact measurements. You're just interested in recording the signals and using like Python or GNU radio to demodulate them and get the data off.
Right.
So that's the RTL SDR. You can find it on Amazon for like $30-$40. It's probably up to 50 now because it's been a while since I bought one. It's receive only if you want. Oh, go ahead.
No, I'm just saying that's a great idea. No, go on, man. I'm fascinated.
Well, I was going to say that's receive only. If you want to transmit signals, you'll need something like a Pluto, which will run you like $200-$300, or a Hack SDR, Hack 1 SDR. That's like in that same ballpark. But yeah, if you just want to do protocol analysis, just get an RTL SDR, $30-$40 on Amazon. You can also use it as like a soft receiver too, right? If you don't have like a radio that can, decode the data, you could, just use it as a soft radio receiver.
You ever worked with LoRa comms?
Yeah, that's what I'm all my time is filled with is understanding LoRa right now.
I really want to implement my own robot internet where each of them is a node and each of them is constantly sending. Could you imagine doing this with no internet? Like that would be pretty amazing, right? But I guess that's what you're working on now. Tell me more, man. I mean, obviously, if this
I
company,
can't give too much away.
Totally
It's
understood.
just really just investigating. We'll say investigating LoRa to, update our wireless security protocol with. So like right now, we're just using a proprietary ASK amplitude shift keying modulated protocol that works at 433 to connect a wireless sensor, like a motion sensor, to a security panel through a receiver. So it's, LoRa and Zigbee are, two candidates, right, to have a modern wireless ecosystem. So
for everyone listening, LoRa, pretty much that just stands for like low, long range comms, right? Long range,
yeah,
LoRa.
yeah, long range.
But
okay.
LoRa is basically. Oh yeah, Eric, feel absolutely free to explain LoRa to us.
Oh sure. LoRa is a wireless protocol that works, between 868. Well, there's actually a Chinese specification that works at 433, but usually for EU it's 868 megahertz, and US it's 915 to 928 megahertz. So it's considered a sub gigahertz, so you get wider coverage, right? Because as you start getting up into microwave frequencies at gigahertz and above, right, Wi-Fi's and Zigbee are 2.4 gigahertz, signal starts getting attenuated, right, more in the atmosphere. So yeah, just being sub gigahertz is ideal for longer range. But the idea too with LoRa that sets it apart from Zigbee is that sort of the gateway and the network and application server can all be separated from one another, right? So like the gateway can actually forward packets to different network servers that are running in the cloud, and those network servers can ultimately deliver the data, the payload data, to different application servers too. But yeah, standard LoRaWAN, everything always connects to a single, actually one or more gateways, but the gateway or the end devices can't themselves retransmit a message, from one end device to another. Something that Zigbee can do though. Yeah,
Fascinating stuff.
yeah. If you have the right antenna too, it's I have a feeling that some of the LoRa sensors we've been looking at have like ceramic antennas on the PCB. I feel like those, aren't going to have as long range as like a monopole that, is outside the body of it or something. If you want the longest range, right, you concentrate the RF energy using a very directional antenna, and you point them at one another, right? That's how you get I think that's how you get like the kilometers of range. But LoRa also has a lot of things too. I think that's one thing I didn't mention, that LoRa has a lot of goodies in its bag to sort of pierce through the noise floor, right? So the way the LoRa modulation works is that it's uses a chirp, and the idea with a chirp is that you're using really the frequency shift, or sort of your frequency versus time, that slope, to encode the data. So you can actually recover signals that are below the noise floor. And LoRa has like adaptive data rates. So if you go down to like SF12, that will send smaller bits of data, but also boost the transmit, and also do some more error correcting, that you can, essentially cut through the noise floor very efficiently.
That's pretty fascinating, man. Just a quick breeze over this. So what we're going to need, I'm going to say it real quickly, but yeah, we need the Raspberry Pi 4 with 4 gigs of RAM. If you have a stronger Pi, that's fine too. But at least this, we're going to need that L298N motor controller, very cheap. You're going to need some kind of power bank, because we're going to have a different power source for the Pi than we're going to have for the motors. We're going to need a fuse holder for that circuit that's controlling the motors. We want to make sure the ground of the Pi is going to be connected to the grounds of this motor controller. So we want to make absolutely sure that nothing can go wrong and fry our Pi or our motors. You know, they're not as expensive as the Pi, but it's better not to fry your motors, you know? So we're going to have this fuse controller. We're going to have an on-off switch, pretty classic there. These are the batteries that we are going to be using. Josephine said she's going to be using AA's, right?
Yep, AA batteries. I checked with the battery holders that I bought, and they fit right in, no adaptation needed. So I've got like a ton of AA batteries, so I should be good there.
Yeah, you got to get to 5 volts, right? But you also
Mhm.
need the current too, which you get by putting the batteries in parallel. So you just need the right
Yeah.
series. But I guess my concern is, I've done some like power budget calculations, like with how much current you would have to source at like max. You're running the motors full duty cycle. I'm thinking like the Pi, is going to draw about an amp at the most if you're doing like heavy calculations. I haven't really looked at the chemistry for like the normal alkaline or batteries, but I think there could be an issue just sourcing enough current.
The specifications in here are 18 watts, PD at least 18 watts, must include a USB to Type-C charge cable. So we got this webcam is $8. I just put the whole thing in here just so that people could see. You do not need an expensive webcam for this. Even when we start doing SLAM, simultaneous localization and mapping, and like computer vision, you can use this and get some pretty decent work out of it. $8. And we got our jumper cables. You're going to need female to female, and you're going to need male to male. Now you can probably get away with, you're definitely going to need one male to female, but if you only have one male to female and you have a bunch of like male to male, you can use the male to male for most of what we're doing. But you need one male to female, and you need at least 8 female to female. The first thing we're going to do, just so that you can see how easy this process is, it's not going to be easy because you're going to get bugs. And you're going to have to solve them yourself. But if you follow these steps exactly, you can do this in probably like less than an hour. So you're going to power up your Raspberry Pi. I didn't put the directions for flashing Ubuntu onto your SD card. I figured, that's pretty easy to find the tutorial for. Just get Ubuntu onto your SD card and make sure you set the network specifications. If you use Raspberry Pi Imager, as this tutorial says, it's going to be very easy to set all the specifications you need, and you won't need to download an ISO like we did when we dual booted, because Raspberry Pi Imager already has links to the Ubuntus that we're going to need. The only Ubuntu it's 2404 is what we're using. Same as on our desktops. This is some of the code where I kind of show you like these are numbered GPIO pins. So this code, I took these segments just so that you can see we are referring to each of these pins in the code so that our programs can successfully communicate to this device what we want the motors to actually do. This is just the Pi, the motor controller, and the motors. This is what they're going to look like. This is the full circuit. So same thing as you saw up here, plus we're going to put this into this slot right here. This is the fuse holder. And the fuse in here, I left it open so you can see the fuse. If you buy your fuse holder, it's not going to come with a fuse. That's going to connect to your on-off, which connects to your batteries that are going to be connected in series. And then that's going to connect back into here. Common grounds between the motor controller and the Pi. And that's all that you need. The power bank is connected directly to the Pi. That doesn't go anywhere else. So that's pretty. I actually put this together since it's so easy and quick. I put it together, downloaded all the code onto the Raspberry Pi, and just kind of like put it here so you can see how it works. Now the install, this is just, I'm not going to mention everything here. I pretty much put all the packages you need right here. I've reproduced it many times with new systems. This is all ready to go. Then you're going to install some initial dependencies, more installs. And at that point, you are ready to power up your robot and start playing with your cat, as you can see in this video. Pretty cool stuff. And I hope, obviously, if the stuff to build this costs money, and I know that it takes a little while for things to actually be delivered, but if we can all have our materials for the next tutorial, we're going to be building robots in a week. So hopefully we'll be able to do that. If even one person's able to get all their materials, I'm going to show that one person how to do this, and everyone else is going to watch.
I'm doing
For sure.
computer science right now and data science, and if I can do robotics as well, all in my one degree, I have all the options, and I can be a very versatile person